Again, geology enthusiasts, we are here today to really synthesize the Earth and the Earth's surface and Earth processes. Let's see, where we're coming from is we have a really good understanding now of absolute time and relative time. So we know how the age of the Earth has been established. We understand that different rocks and systems can be dated geologically and how that can be done. So that's a really important foundational concept of historical geology. Now I wanted to kind of expand our view of the planet by looking at some maps and talking about some of those Earth system processes. So we're looking at an elevation map on the screen whereby the higher elevations are in red and the lower elevations are in blue. So you'll notice that that Greenland is red and Antarctica is blue, is also red. So the question remains, why is that? And your answer back to me is that there's ice on those surfaces that are at higher elevations. So it gives them some topography. So we would think that their systems are flat, but actually the ice sheets can be up to anywhere from 5 to 6 kilometers in thickness in some parts of those ice sheets. So significant rises in elevations. Then we can look at the organization of the globe in other respects. So you can see on the North American continent, there's something that's called the North American Cordilleran, which ranges from Alaska all the way through Mexico to Central America. And localized, we call that the Rocky Mountains, right, in North America. So areas of higher elevation. In South America, you can see the Andes Mountains. And then in going through India, you can notice the Himalayas. And the Himalayas are the highest mountain range at an elevation greater than 28,000 feet above sea level. So we can look at this map and ask some questions as to why there are these higher elevations. And I'm going to let you think about that. We're going to come back to those concepts in a later lecture. But right now, let's review the parts of the Earth. And so when we make some comparisons between the continental crust and the oceanic crust, so the crust on the exterior of our planet, we organize that into different rock types and densities and thicknesses. So when we talk about rock type, you're going to be familiar with this now. We talk about igneous rock groups. So we generalize that as saying that continental crust is granitic. So you remember seeing granitic. It's an intrusive phaneritic rock that is made of potassium feldspar, quartz, and biotite. And so we generalize that as being our continental crust. And then we look towards the oceanic crust. And we call that basalt, and that is aphanitic and forms extrusively. Those two different rock types have different densities. So the density of basalt is greater, and the density of basalt is going to be 3.3 grams per cubic centimeter. And the density of granite is going to be lighter at 2.7 grams per cubic centimeter. And then when we look at the thicknesses of those, they range also, whereas the density, the thickness rather, of the continental crust is going to be anywhere from 13 to 40 kilometers in thickness, and the oceanic crust is going to be anywhere from 8 to 10 kilometers in thickness. So the continental crust is much more thick than is the oceanic crust. And just to review, you've probably seen this before, but we live on a planet that is differentiated, and a differentiated planet means that it's separated into parts. So if we start in the interior, we have the inner core, and that's considered to be solid or metallic. The outer core is liquid. The lower mantle is considered to be plastic. The upper mantle is considered to be solid, as well as the crust. The upper mantle and lower mantle are separated by something that's called the Moho discontinuity line. So there's a divide that becomes pretty important. When we talk in terms of the crust and the upper mantle, we call that the lithosphere, and everything below that is the asthenosphere. So the lithosphere is on top of the asthenosphere. It's separated by the Moho or the Mohorovic discontinuing line. So my question for you then is, obviously we know an awful lot about our differentiated planet. So we understand that it's separated into parts and it has different densities and properties. So my question to you then, what evidence is there to support physical characteristics of the Earth's interior? So like, how do we know that? Like, how do we know that the continental crust is on average 35 kilometers in thickness and that the oceanic crust is 7 miles in thickness? It's pretty interesting because there was a pretty big Science Foundation grant that Germany received, and they were going to give it their old college try and try to drill all the way to the core. And what we know is that it's probably impossible. Or there's fantastic sci-fi movies about that. But they made it about 7 miles into the continental crust. And the problem is that as you go deeper into the Earth's surface, the pressure increases as well as the heat. So for every kilometer deep you go, the temperature rises about 10 degrees C. So it can get very hot, and there's not really anything that can maintain that drill before it eventually melts, right? So if we can't drill to the Earth's surface, then how do we know some of the physical properties? And you can reflect on what you already know about Earth history and Earth science, and you may come up with the idea that, well, we know an awful lot about the interior of the Earth because we're able to measure it in seismic waves and seismic energy. So the energy that is released during an earthquake event from the focus of an earthquake can be measured. And so we measure that by seismographs, and we've been doing that since 1901. So with the ability to measure seismic waves and how they move about the globe from different seismic stations, we are able to then delineate the density of the crust. So on this figure here, you're looking at velocity on the x-axis and depth on the y-axis. And so you're starting at the surface on the y-axis at 0, and then you're going through these different layers that we have already described. So you're going through the crust, and then the upper mantle and the lower mantle, the outer core, and then eventually the inner core is at the bottom of that. And what you can recognize is that there's 2 different waves. So when you have an earthquake originates at the focus, and energy is released in the form of primary waves, or P waves, and S waves, which are secondary waves. So both of these generate at the same time, but they move at different rates and have different characteristics. So a primary wave can go through any type of medium. It can go through a liquid, a solid, or a gas. A secondary wave, an S wave, cannot go through things that are liquid. So we said that our outer core is liquid, and when we look to measure the S wave component, it doesn't show up on a seismograph going through the liquid outer core. In addition, P waves and S waves travel at different velocities, and they travel at different velocities through things that have different densities, and that's what this figure is showing you too. So the way these waves are refracted off of these different parts of our planet can be measured and monitored. So that's how we know so much about the interior of our Earth. As I mentioned, S waves don't go through things that are liquid, and you can see something called an S wave shadow zone, essentially. So if you're on the right side of the planet and you have a seismograph on the opposite side of the planet, you won't be able to communicate with each other. So your seismographs wouldn't show the same thing because it can't pass through the liquid core. So the waves are refracted off of that. If you're interested to hear more about this, you should take my physical geology class, because we really dive into earthquakes and seismic energy. So we said that when we're looking at these different parts, we've established a lithosphere and an asthenosphere. So the lithosphere, again, and here's our definitions on the screen so that you can write them down into your notes. The lithosphere includes the rigid parts of our planet, so the crust and the upper mantle, and then the asthenosphere is the lower mantle. So a small portion of our Earth is the lithosphere, and that's going to contain your continental crust and your oceanic crust, and then below that is going to be the asthenosphere. And again, they're separated by the Moho line. So my question then for you, before I move to the next screen that has the answer, my question for you is, why doesn't the solid lithosphere sink into the asthenosphere? Right, so you have something that's rigid and solid and is setting on top of something that's liquid. So why doesn't it sink into the asthenosphere? And I'm going to tell you that there's two different answers to that question. Have you ever thought about it? So the asthenosphere, the lower mantle, is essentially where the magma comes from in volcanic activity to form extrusive igneous rocks. And the answer is, well, it's a density-driven system. And if we remember the equation for density, we say that density is mass over volume. So the asthenosphere is both greater in mass and larger in volume. So it's able to support the lithosphere on top of it. The second part of that is that in the lower mantle, there are a system called convection cells. And so convection cells are also density-driven systems whereby you have heat that's moving towards the surface, and as it does that, it cools and condenses and falls down. So these are called convection cells. And so these convection cells have movement, and we often see and associate convection cells with divergent plate boundaries and also with hotspots. And what's interesting is that very little is known about convection cells. So we're kind of up against one of those geological boundaries where we understand the process, but we understand and can map where they're located, but there's such a randomness in the size of these and the location of the hotspots. There's still a lot to be learned. So I'm really curious that in my lifetime, how much more we can find out about these convection cells. And of course, there's a mantle plume underneath Iceland, so that makes me even more interested. So we have established the parts of the Earth, the interior and the exterior. We have established the terms lithosphere and asthenosphere, and we have done that because we're interested in plate tectonics. And as we move forward in historical geology, we're going to be very interested in studying the effects of plate movement. Because, of course, the plates are going to move about the globe over the course of geologic time because these plates have never been stagnant. They've always been dynamic. So what you're looking at on the screen right now is a modern-day plate tectonic map. There are 7 major plates and 12 minor plates. And what we've learned is that these plates are moving by convection cells. So they are, that density-driven system is going to be one of the major drivers of plate tectonics. On this diagram, and we're going to play around with this in class, you are going to notice the black sawtooth edge. And so you've got these triangles and the black line, and that's going to represent a convergent plate boundary. So go ahead and write that down. And then the bar type formation is going to represent a divergent plate boundary. And we're going to talk more about what that means. But I just need you to be able to look at that map to identify convergent plate boundaries and divergent plate boundaries right now. And then the big arrows represent the overall direction of movement. So the overall movement of a plate. And I'll post this map online so you can have access to it and go ahead and print it out. And I'll bring some copies to class. So when we're looking at a plate tectonic map, one of the questions we're asking is like, where do the continents end, right? And so in terms of geology, the ending of a plate is at the plate boundary. So we can even look at the North American plate on this map. It's highlighted in purple. So the western coast ends in a convergent plate boundary, and the eastern coast ends in a divergent plate boundary. Other terms that we use when explaining convergent and divergent plate boundaries. Convergent plate boundaries are known as active plate boundaries, so where there's active movement, and divergent plate boundaries are known as where they are passive, so passive plate margins, where there's little activity that's happening. So we can talk a little bit about divergent plate boundaries. Divergent plate boundaries are plates that are moving apart from one another, so they have spreading. And usually that spreading is initiated by a body of magma. And so you have essentially a piece of crust, and it can be continental or it can be oceanic, that's being pulled apart. And one of my favorite places in the world is Iceland. Iceland, that's how they say it. Iceland. And what if we went back to that plate tectonic diagram to take a look, Iceland is sitting directly on top of a divergent plate boundary. I'm going to go back. So here's the North American plate on the left, the Eurasian plate is on the right, and the island of Iceland is sitting directly on top of a divergent plate boundary. So if you're looking to buy property, I know I have some business students in my class, then you're going to want to buy property along the divergent plate boundary, because what's happening is that area is getting bigger. And then eventually you're going to end up with oceanfront property that you can get relatively inexpensive. So the Eurasian plate is moving away from the North American plate at a rate of about 1 inch per year, or about 13 miles per million years. So get your mind around that. And that takes us back to our early discussions about rate and time, like how fast is fast, how slow is slow. So 1 inch per year doesn't seem like much, but when we total that up, 1 inch per year equals about 13 miles per million years. So it's significant in the geologic history of Iceland. So what typically happens is when you have this rifting, and so you've got these plates that are being pulled apart, and what happens is the area that's in the center is going to sink, and that's called a rift valley. So you end up with a rift valley in the center of that divergent plate boundary, and as it gets lower and lower, it's obviously going to be infilled with water, because it's going to be lower than the surrounding areas, and it's also going to act as a basin for river systems, because it's, again, like a catchment. So, and eventually what can happen is that it can eventually get completely pulled apart. So this lower picture is of Iceland, and when we talk about divergent plate boundaries, we also term it as the mid-ocean ridge. So you're imagining a divergent plate boundary that goes all the way around the globe. So here's Iceland, there's a divergent plate boundary, and anywhere where you see this bar is called the mid-ocean ridge. So you have these divergent plate boundaries that are separating the basement of the ocean. And what we said was that oceanic crust is made of basalt. And so at those rift valleys, that are being pulled apart, it acts as a conduit for magma to come up to the Earth's surface. So magma in the form of basalt is infilling those rift valleys. So MOR, mid-ocean ridge, locally to Iceland, they call it the mid-Atlantic ridge. And that's what you see highlighted on this diagram here. And that's just because it's in the Atlantic Ocean. Additionally, what you'll notice is triangles on this diagram, and this is pretty common on divergent plate boundaries, and it's the idea that you can have active volcanism at those divergent plate boundaries, and that makes sense because you're pulling the plates apart and you're allowing for magma to come up to the surface. So Iceland, again, is about the size of Kentucky. There's 32 active volcanoes on that island, and that makes a whole lot of sense now considering the divergent plate boundaries. Iceland is one of the only places in the world where you can see a divergent plate boundary exposed at the Earth's surface. And that's what you're seeing here. So this is a picture in Reykjavik. You're imagining you're looking out to the ocean, and you're standing on top of the mid-ocean ridge. And if you move into the interior, oh, this is a good picture. So on this picture, the Eurasian plate is on the right and the North American plate is on the left. So you see part of that spreading. And if you go further into the interior, there's a bridge that links the Eurasian plate to the North American plate. So you can be like, hey, friend, on the Eurasian plate. Hey, I'm over here on the North American plate. Don't forget your passport. It's funny. Don't forget your passport. And then where are you when you stand in the center? Oh my gosh. I never thought about that. It's like you're nowhere. Anyway. You're in the Rift Valley. That's where you are. So, yeah. So eventually, Iceland will be completely pulled apart, and it will be 2 islands. One of the things I want to go back and point out on this map, is that you see this Y feature, and we'll talk about why that is. Gosh, I'm funny today. So you're pulling it apart, and eventually you get a new ocean basin, and that's what we're starting to see here in the interior of Iceland. So my question for you then is, how do divergent plate boundaries form initially? And I've already kind of hinted at this, and you're thinking about that at home, and you're like, I wonder why divergent plate boundaries happen and how they form initially. And again, it has to do with that body of magma being able to come up closer and closer to the surface. So this is called a triple point junction. So you're imagining a magma plume or a hot spot, and it's rising. And if you have oceanic crust or you have continental crust, but it ends up showing up as topography on the Earth's surface, and eventually it's got to crack, like that pressure has got to be released. And so you end up with a rift. We mentioned a few times about the Yellowstone hotspot, and this is what's predicted. So for sure, you'll probably have a major volcanic event. Will it happen in our lifetime? Not sure. But what's happening is that magma plume will eventually cause enough pressure that it's going to have to crack the Earth's surface. And when it does crack the Earth's surface, it cracks in a Y. So that is called a triple point junction. And so in Iceland, we see that Y. So we see the triple point junction. The hot spot is just under the southern end of Iceland. The mantle plume in Iceland is about 200 miles in diameter. And in other places in Iceland, you see that release. You see cracks that are happening at the Earth's surface as the divergent plate boundary moves and as the magma comes up to the surface. In other parts of the world, we also see this. So this is a picture of focusing on Africa, and you have the Arabian Peninsula up in the north, and then the Arabian Peninsula is separated by the Red Sea and the Gulf of Aden. And so down here is Uganda, Tanzania, East Africa, Uganda, Tanzania, and Kenya. So I'm going to zoom out to this map. So you've got the Arabian Peninsula, and the Arabian Peninsula is separated from the African plate by a divergent plate boundary. And this is also happening real time. So just to get your mind around it, right? Like the Arabian Peninsula was part of Africa. Then you get a magma hotspot. It fractures. There's a divergent plate boundary that's separating the two at modern day. So you have the Red Sea, the Gulf of Aden, and if anybody has had the fantastic chance to go to the East African Rift Valley, the East African Rift Valley is a low-lying valley. It's on a divergent plate boundary. It is the home to the volcano Kilimanjaro. So one of my favorite hikes. It takes about 3 or 4 days to get to the top. It's a tough one, but always worth it, right? So another thing that's in the East African Rift Valley is the Serengeti. The Serengeti. So let's take a look at what that looks like. So here is one of my study abroad trips that I took to Africa, and we're hiking so when you have a divergent plate boundary, you have highlands, and then you've got the Rift Valley. So we're hiking on top of one of the highlands here and looking down into the Rift Valley. Here's another perspective. Wow, look at that. So this is in Tanzania. This is near the Ngorongoro crater. I don't know if you can pick up that pink hue out here, but those are flamingos that migrate through because there's a low-lying basin that's holding water at the bottom. These are zebras. And so you can see like the rift in Iceland is relatively new, and so the upper portions, which are called horst, we talk about that more in physical geology, but the upper portions of that rift are much higher here because it's a much older divergent plate boundary. And in this picture, you can see that our hot air balloon shadow off in the distance. This is sunrise flying over the Serengeti, and just a spectacular perspective of this rift. Additionally, important to historical geology is the East African Rift Valley is home to some of the oldest hominoid fossils on the planet. So early descendants are found there, and the name escapes me. I went to that museum. East African Rift Valley. Can't think of the researchers. Dang it. And it's a female. Anyway. So divergent plate boundaries are fantastic. Do you know what else is fantastic? Convergent plate boundaries. Again, we're going to go through this relatively quickly. If you love this stuff, please take my physical geology class or my geomorphology class. Convergent plate boundaries are when two plates come together. So they're converging and they're moving together, and the heavier plate will subduct. So when you have plates collide, something has to give, like the energy has to go somewhere. And what we know about our planet is that it's not getting any bigger and it's not shrinking, it's staying the same size. So if you have a divergent plate boundary, that divergent plate boundary has to end at a subduction zone. Because essentially what's happening at the divergent plate boundary is you're creating brand new crust, like brand new literally, and that the edges of that crust have to subduct somewhere. And that subducts at a convergent plate boundary. So we mentioned our continental crust is made out of granite, and our divergent plate crust is made out of basalt. And we said that basalt is heavier. It has a greater density. It has a density of 3.3 grams per cubic centimeter. Our continental crust has a density of 2.7 grams per cubic centimeter, and it's considered to be granitic. So anytime you have oceanic crust converging with continental crust, the oceanic crust is heavier and will subduct. And I've been holding this. Oh, this is one of my very favorite samples that I have here in my home office. And you're looking at a collisional plate boundary. I can't even believe I have this. So you've got granite, and that granite is colliding with the basalt. Isn't that fantastic? Look at that from the side. Look at that. I did not find this. This was a gift. Yeah, I love this so much. It's one of my favorite possessions. Anyway, so the basalt is heavier and will subduct underneath the granite. And this is like a classic, like textbook example. So we're thinking in terms of South America. So you've got the Andes Mountains, you've got an oceanic plate that's converging with the South American plate. And of course, when you have convergence, you have uplift. And that uplift in this scenario is going to be the Andes Mountains. And we call them an active plate boundary because you have active subduction and you have active mountain building. So that's scenario one. Continental crust collides with oceanic crust. Scenario dos is when you have a continental crust colliding with another continental crust. This is the classic example of the Himalayan mountains. So you have India that's colliding with the Eurasian plate to get uplift. And in this scenario, continental crust is colliding with continental crust, and so you have granite colliding with granite. And so in this scenario, what's going to happen is the crust that is older is denser, and that will be the subducting plate. So India is heavier and will subduct underneath the rigidity of the Eurasian plate. And then the last one is ocean to ocean convergent plate boundaries. So two layers of basalt that are colliding with each other. Same type of scenario. The one that is older is going to be more dense and will be the one that subducts. And so our Aleutian Islands are off of Alaska, and you end up with an island arc in this convergent plate scenario. And of course, the Aleutian Islands are still volcanically active. The last time that there was a major eruption was in 1964, and it initiated a major tsunami that overran certainly parts of Canada, British Columbia, the state of Washington, Oregon, and Northern California. It was the last major tsunami event in North America. And it was the event that instituted the building of a warning system, a tsunami warning system. In the Pacific Ocean. So when you have convergent plate boundaries, what can happen is that the subduction angle can change over time. So I want you to take a look at this map just to get your mind around this. There's something that's called the Pacific Coastal Range. Beautiful, beautiful part of the country. And it is at the edge of Washington State, Oregon. And then in the interior, you have what's called the Cascades. And so the Cascade Mountain Range includes the Seven Sisters. So the Seven Sisters are Mount Rainier, Mount Baker, Mount St. Helens, Mount Hood, Mount Craters on here, Mount Jefferson, Mount atoms. Those are lesser, smaller peaks, but there's 7 volcanoes essentially that make up the 7 sisters of the Cascades. What had happened in this scenario is that the Cascades are still volcanically active. So there's a convergent plate boundary that's on the west coast that formed the Pacific coastal range. But what happened is, over geologic time, the subduction angle has lessened. And so the volcanic activity has moved to the interior instead of being on the edge of our western seaboard, which is interesting. So that's why we have internal volcanism within the United States. So just for the remainder of the lecture, I want to bring us back to the plate tectonic diagram, and let's just play around with it and try to synthesize it, right? So if you're looking for a convergent plate boundary, my question to you is, where do you see that? And so we can look for sure at the Aleutian Islands up here in the north is a convergent plate boundary. The Himalayas is a convergent plate boundary. And then we can ask the question, well, where are some of your divergent plate boundaries? And so over here in Iceland is an example. And what you'll notice is that the entire plate of Antarctica is surrounded by a divergent plate boundary. And what's particularly interesting for historical geology when we start to think in terms of how the plate has evolved over time, the planet has evolved over time, Antarctica has always been in the southern hemisphere. So no matter when the Pangea plates come together, Antarctica has always been on the southern hemisphere. So that's going to explain a lot about what we see in terms of the fossil record. It's always been cold or colder, not always glaciated, but always been more cold than other places on the planet. When we come to lecture, we're going to tease out this a little bit more, and I'm going to bring you a copy of this. You'll see this on exam 1 for sure. So we'll go ahead and play with that and ask some more questions about it. I think it's been a great summary of plate tectonics for Geo 102. You've been a wonderful audience, and I'll see you later in the week. Take care.